In this video, we're going to identify the properties of asymptotes, points of discontinuity, zeros and y-intercepts, and other known points for 9 parent functions. We'll begin with linear, and we'll identify its asymptotes, which is sort of funny because there are going to be no asymptotes for a linear function. An asymptote is a line or lines where a curve approaches as something about it increases or decreases without bound. You can have a horizontal asymptote where essentially the curve flattens out as x goes to more positive infinity or x goes to negative infinity. You can also have a vertical asymptote as x approaches a number but the heights go to infinity or negative infinity. We have none of that going on here with a linear function. In fact, let's just stick with asymptotes right now and realize that both the quadratic and the cubic also have no asymptotes. They are polynomials, and polynomials do not have asymptotes. Another element is finding the points of discontinuity. Think of a point of discontinuity as where you have to pick up a pen or pencil when drawing a graph. As long as you can keep drawing the graph, then that's continuous. The moment you have to pick up the pencil, that's point of discontinuity. Again, these 3 polynomial functions all have no points of discontinuity. Once you start drawing it, there is no reason to pick up the pencil. Let's go ahead and look at the zeros of each of these graphs. Another element of being a polynomial is that they all share the same 0 and y-intercept. Literally, their graphs all cross at the origin. So their zeros are going to be at x equals 0, and therefore their y-intercept will be at y equals 0. Same is going to happen for quadratic and for cubic. The one property that will be different is the known points. They share 0, 0. They share 1, 1. After that, it's different. For instance, if I would go and plug in 2, well, I would get 2 out for the linear parent function. On the other hand, if I would put in 2 for the quadratic, I would have to go 2 squared and come up with 4. If I had 2 for the cubic, I would have to go 2 cubed and come up with 8. Another aspect that will be different is how negatives are treated. If I go negative 2 will give me a negative 2 for a linear function. But a negative 2 when squared is positive 4 for the quadratic parent function, while a negative 2 plugged into a cubic, a negative times a negative times a negative is still a negative. Known points for a linear function essentially is where all the x and y coordinates are equal to each other. So you have 0, 0, 1, 1, 2, 2, 3, 3, negative 1, negative 1, negative 2, and negative 3, negative 3. For a quadratic, you could have 0, 0, 1, 1, 2, 4, 3, 9, 4, 16, where all the y's are the values of x squared. And then you could also have negative 1, 1, negative 2, 4, negative 3, 9, negative 4, 16, negative 5, 25. Remember, this corresponds to our range, where all the y coordinates are non-negative. And then finally, cubics would include 0, 0, 1, 1, 2, 8, 327, 464, and then you also have negative 1, negative 1, negative 2, negative 8, negative 3, negative 27, and you could have negative 4, negative 64 if you wish as well. We'll move on to square roots, cube roots, absolute values. In the case of asymptotes, none of these graphs has an asymptote. No point does this graph ever go height-wise at a specific value, nor does it sort of flatten out at a specific height as x approaches either infinity or negative infinity. So we'll leave it at that. In terms of points of discontinuity, the cube root and the absolute value, it's obvious that you can continue drawing the graph at all times. When it comes to the square root parent function, some students are concerned because you don't start graphing until you get to 0, 0. Don't worry about where you start. It's what happens as you graph. The moment I start at 0, 0, do I ever actually have to pick up the pencil? The answer is no, and therefore points of discontinuity do not exist. Let's move on to zeros and y-intercepts. All 3 of these parent functions, once again, are crossing at the origin 0, 0. Therefore, their zeros are going to be at x equals 0, and their y-intercepts will be at the height of y equals 0. Now, known points, we have to ask ourselves, what values should we know about when it comes to square roots? So, if we look at 0, we take the square root of 0, we get 0. So that will be a known point. We should also understand that the square root of 1 will give us 1. I don't think I really want to worry about 2 because the square root of 2 is going to be an irrational number, a number that will not necessarily be friendly to graph. In fact, it's going to take me all the way to get to 4 before I can find a nice square root again that produces an integer, in this case 2. And again, I will do this with 9 so that I can take the square root of 9 and come up with 3. And so some known points for a square root function include 0, 0, 1, 1, 4, 2, 9, 3, and 16, 4. But if you recall, the square root function ended up being the inverse of the quadratic, or x squared, then it shouldn't come as a surprise that the x and y coordinates of the quadratic are showing up here in reverse order, or at least the ones where x is non-negative. On the quadratic was 0, 0, 1, 1, 2, 4, 3, 9, 4, 16. We have 0, 0, 1, 1, 4, 2, 9, 3, 16, 4 in the square root function. When it comes to the cube root, we're going to do something very similar. We're going to need to find values that work well if we want to have those points kind of memorized. And so we'll need to take 0, and the cube root of 0 is 0. Just as 1, put that in, the cube root of 1 is 1. But we can't use 4 because the cube root of 4 is going to be an irrational number. It's going to take all the way to 8. The cube root of 8 is 2. Then we'll move on to 27, and we'll realize that the cube root of 27 is 3. Unlike square roots, you can also use negative numbers as well. So we could use negative 1 and take the cube root of negative 1 and get negative 1. We could take the cube root of negative 8 and come up with negative 2. We can take the cube root of negative 27 and come up with negative 3. And that's how we get those particular points as well. Let's move on to the absolute value parent function. If you analyze the graph, you may see that the right half of the v-shaped graph is the same as the linear function. Therefore, certain known points like 0, 0, 1, 1, 2, 2, 3, 3 would also be here as well. Absolute value takes a non-negative form of your x value. Since 0 is neither positive or negative, it's just going to stay 0. On the other hand, if you plug in negative 1, the absolute value of negative 1 is 1, just as negative 2's absolute value is positive 2. And that's how we get the known points negative 1, 1, negative 2, 2, and negative 3, 3. With these last parent functions, some of these properties are going to be different than before. And we'll begin with hyperbola and the asymptote, because as we look at the curve, we recognize that as x is either going to positive infinity or negative infinity, the height of that curve is approaching 0, and it seems to be flattening out. This would be a horizontal asymptote, and that would occur at y equals 0. Just as, if we look at how x is approaching 0, the heights all of a sudden are now either going to positive infinity or negative infinity on both sides. This would be a vertical asymptote of x equals 0, and those would be our two asymptotes. The same thing applies when it comes to inverse square. Although the graph never goes into the negatives, both the left and right side flatten out as they go to their appropriate infinities, and we get a horizontal asymptote at y equals 0. And once again, as x approaches 0 from either side, the heights in this case both go to infinity, but that still means we have a vertical asymptote at x equals 0. Although the greatest integer function is very disconnected, which we'll get to in a moment, it does not have any particular asymptotes. But let's stay with the greatest integer function as we move to points of discontinuity and understand what happens here is what we have is called jump discontinuity. Literally, the graph is jumping at different heights. And it occurs at every value of x, where x is an integer. And that's pretty much what we want to say. We have an infinite amount of discontinuity, and it occurs at every integer value of x. If we move back to hyperbola and inverse square, in both of these cases, when you have a vertical asymptote, you have what is called infinite discontinuity, and it occurred when x was equal to 0. we'll move to zeros and y-intercepts, which is another case of being interesting because you can't actually plug in 0 because you'd be divided by 0. And you'll notice that the graph isn't defined on the y-axis. Therefore, these graphs have no zeros and no y-intercepts. Moving back to the greatest integer function, if we look at the graph, we see that it does cross at 0, 0. Therefore, the y-intercept is at 0. However, when we look at the zeros, we find that not only does 0 happen to produce a height of 0, there's an infinite number of points between 0 and 1. Now, it doesn't include 1 because once we get to 1, we jump up to the next height of 1. So our zeros occur with all the points between 0, including 0, up to 1, but not including 1. And as I said, we already have a y-intercept of y equals 0. So we come down to known points for the various graphs. Well, a hyperbola essentially is like having a reciprocal because whatever we do, we're going to take 1 over that. So if we plug in 1, we get 1 over 1, which is 1. If you plug in 2, you get 1/2. 3 gets 1/3. Now, if we happen to plug in a fraction, we would take the reciprocal of the fraction. So I guess 1/2 would then lead to 2. Same thing happens with negative numbers. Negative 1's reciprocal is negative 1. Negative 2's reciprocal is negative 1/2. Negative 1/2's reciprocal is negative 2. Moving on to the inverse square, we have a little bit more work involved because we also have to square the number. So if we plug in 1 and we go 1 over 1 squared, we'll get 1. On the other hand, if we plug in 2, we're going to have to go 1 over 2 squared, which is actually 1 over 4. The same thing is going to happen when we plug in negative 2. We're going to have to go 1 over parentheses negative 2 squared, and that's going to end up being 1 over positive 4 as well. So let's just cut right to the chase. The points that would be included in an inverse square include 1, 1, 2, 1/4, 3, 1/9. You also could have 1/2, 4, negative 1, 1, negative 2, 1/4, negative 1/2, 4. And to wrap up, let's look at the greatest integers known points. The problem is the ones that we want to know are the obvious ones. 0, 0, 1, 1, 2, 2, negative 1, negative 1, negative 2, negative 2, because integers round down to themselves. But it's the decimals that are the more interesting ones because they get rounded down, which produces this jumping effect that we see in the graph. To summarize the known points property, I'm not concerned that you don't know, let's call it the obscure ones. I'm interested that you recognize certain points that show up in multiple parent functions. For instance, 0, 0 shows up in 7 of the 9 parent functions. The only ones it doesn't show up on is hyperbola and inverse square. On the other hand, 1, 1 shows up in all 9 parent functions. Meanwhile, when it comes to x equaling negative 1, some of them have 1 as its y value, and other times negative 1 as its y value. You should know the difference for those. And this concludes the properties of asymptotes, points of discontinuities, zeros and y-intercepts, and other known points for 9 parent functions.